In this video, I want to introduce the notion of a basis for a vector space. Now, before we get to the technical definition, I just want to say that you can think of a basis essentially taking the smallest piece of a vector space from which you can rebuild the whole thing. Now, let's jump in here. And actually, before we get to the definition of a basis, I'm going to throw a couple other definitions in here first. And I'll admit, I'm only doing this because this is the way our textbook does it. I actually think these two definitions can wait until the next section, but we'll throw them in here for now. We say a vector space is finite dimensional if there exists a finite set of vectors that span the vector space. And if it's not finite dimensional, then it must be infinite dimensional. Now, the notion of dimension here, we haven't defined at all. This is sort of our first definition of dimensions, finite or infinite dimensional. In the next section, we will actually talk about specific dimensions to be able to say, oh, this vector space is 3-dimensional or 5-dimensional or whatever. But for the moment, it's just finite or infinite. Okay. Some examples, Rn is finite dimensional, right? You can think about a spanning set for, let's just say, for R2, right? You could use what we call I and J, 1, 0, and 0, 1 span that space. Pn, polynomials of degree n or less. So 1, x squared up to xn would be a set that spans Pn. And notice that was finitely many things that I listed. Matrices, m by n matrices, it turns out is finite dimensional. The set of vector spaces, on the other hand, is infinite dimensional. And many of the subspaces are also infinite dimensional. Pn, of course, is a subset of the set of all the set of all functions. But it's finite dimensional. But when you look at continuous functions, that's infinite dimensional. Functions with first-order derivatives, that's infinite dimensional. Second-order derivatives, that's infinite dimensional. Functions that have all of their derivatives, that's infinite dimensional. There's just huge vector spaces. But then within those, there are subspaces that are finite dimensional, as Pn is finite dimensional. All right. Now, I think we're ready for this definition. We say, let's slide it all the way up here. We say that if you've got a set S, which is composed of vectors v1, v2, ve, is a set of vectors in a finite dimensional vector space V, then S is called a basis if two things happen. One, S has to be a spanning set for V, and two, S has to be linearly independent. So this puts together the two most recent concepts we've dealt with, linear independence and spanning. So to say that S spans V is to say that everything in V can be written as a linear combination of those n vectors. To say that they're linearly independent is to say that none of those vectors can be written as a linear combination of any others, right? So in this way, you're saying that everything in V can be, this is a theorem that we'll have to prove in a subsequent video, but the idea here is that everything in the vector space V can be written as a linear combination of these things, and these things by themselves are not dependent on each other, right? You can't make one a linear combination of the others. If you could, then you could throw it away. And again, this we'll discuss further, and have a smaller set. So this essentially whittles it down to as absolutely small as possible. Okay. And the whole finite dimensional thing, the only reason that I think those definitions are given in the book is because within their definition of basis, they're saying you have to be in a finite dimensional vector space. Well, personally, I think they didn't need to say that because they say this is a finite set of vectors and it spans the space. So the inference here is that it has to be a finite dimensional space without actually saying it, because you're saying it can be spanned by a finite set of vectors. whatever. Okay. Here's some examples. In R3, the standard basis, 1, 0, 0, 0, 1, 0, 0, 0, 1, right? Actually, in Rn, you can do a similar thing where you take n vectors, one each that has all zeros except a 1. So one of them in the first place, one of them in the second place, one of them in the third place, in the fourth place, in the fifth place, all the way up to the nth place, right? Every one of those vectors has 1, 1 in them and zeros everywhere else. And that turns out to be a basis for Rn. Right? Likewise, Pn has a basis consisting of 1, x, x squared, and so on up to xn. Apparently that period should be a comma. I mentioned that up above that Pn was finite dimensional because this was a spanning set. Not only is it a spanning set, it's linearly independent, so it is, in fact, a basis. Right? We will need to look at some examples here and some theorems about bases, and we will do that in the next video.